All right. So we've talked about Leibniz rule for how to calculate um, the rate of change of integrals that have boundaries that move. Now I want to do the same thing in 3 dimensions, but add some additional complications to things as well. So in fluid mechanics, we'll often be interested in identifying a control volume and doing our integration over control volumes that are, somehow associated with the geometry of the problem that we're solving. But at the same time, we're interested in applying those to laws of the universe, so like conservation laws that are not really written for a control volume, they're written for a fixed amount of material. So, for example, conservation of mass, is conserving, a fixed chunk of material that we identify. And so we need to figure out how to deal with that. So here's what I'm going to do. I'm going to derive a way to do that called the Reynolds transport theorem. And the derivation starts like this. So let's identify a control volume at time t. So that'll be the red dot dashed line here. So I have a control volume that actually potentially moves in some way with time. For example, if it's tracking an object that is moving. At the same time, we're going to identify a fixed chunk of material, or not a fixed chunk of material, a chunk of material that at time t has exactly the same shape as the control volume. So at least at the initial time that I'm going to identify here, it has the same shape as the control volume. But that material may also be flowing, right? So if the material flows, it may move that the outer boundary of that material volume or the control surface might, or not, the material surface might move with time. And the control volume and the material volume don't necessarily have to move in the same way. That's the complicated part. All right, well, since both of these surfaces are the same at time zero, at least at time zero, what I can do is identify, so if I have like a little patch of area on the outside of that volume, either volume, it'll have an associated unit normal that I'm going to call n hat. And that's, by definition, we're going to call that an outward facing unit normal, which since it's a closed volume, you can always identify the outer surface. So there's an outward facing unit normal at that point. And then at that point on the surface, the control surface and the fluid, like the material, don't necessarily have to move in the same way. So the fluid might have a velocity v sub f, and the control surface itself might have a different velocity, which is I'll call v sub cs for control surface. So then what we need to do is figure out what happens when I move an additional time delta t. So both surfaces are going to change positions at time delta t, after time delta t, and let's identify what happens at that point. All right, so here's a sketch of those control volumes at a point in the future that's not very far into the future. Let's call it t plus delta t, so an infinitesimal time into the future. Those two surfaces moved by some amount, so the fluid moved a little bit and it deformed, and the control volume may have also moved a little bit and deformed. And those two volumes or surfaces are no longer coincident. Now, when I write, so what is our goal here? So our goal is to talk about an integral. So like let capital F be the integral over the volume, either volume, of a quantity little f dv. So like, for example, I'm often interested in calculating the total mass of a chunk, in which case I would have to, for example, integrate over the density. Integrate that over volume and you get mass. So like the pattern here is that capital F is an extensive property and little f is an intensive property. So in this case, I'm writing it per whatever the intensive thing is, I'm writing it per unit volume. When I write conservation laws, what I really care about is the rate of change of, let's call it capital F, for the material, right? So like conservation of mass is written for conservation of the material. And conservation of linear momentum, for example, is for a fixed chunk, a fixed amount of material. So what I need to do is calculate the rate of change of that integral, so capital F, applied to the material. So that's the stuff that is shaded in blue in both the first and the second images there. So in order to take that derivative, what I really want to do, so that's really the crux of Reynolds transport theorem, is figuring out how to take that derivative when I'm actually going to do the integrations with respect to the control volume, like the red thing. How do I relate these two things? They're not the same. Okay, so here's the trick. Okay, so the derivative, df dt of the material is equal to, well, 1 over of delta t times the difference in capital F of the material between those two time points. Okay, but I would like to be able to write those in terms of integrals done over our control volume, because that's the thing that, as an engineer, I'm going to make a picture of my control volume, and I'm going to try and do the integrals in that region. So are these two things related in any way? It turns out that they are, and that's what the Reynolds transport theorem helps us do. So it's a little bit hard, it can be a little bit hard to see, I think, but if I think about that first term, capital F of material at t plus delta t, I can break that into three components that mostly have to do with the control volume. All right, and here's how you do that. So when I look at the right upper figure, what I see is that most of the blue region still resides inside the control volume, i.e. the red region, but not all of it, right? So as an approximation, like to first order, those two integrals are actually the same. Like the material derivative, or the value of F material at t plus delta t is almost equal to F of the control volume at t plus delta t, but there's a difference, which is that some material flowed across the red interface during that time. So that's the thing that I'm highlighting here with the sort of pink-ish color. So there's a portion that's missing from that integral, and that's stuff that flowed in across the control volume boundary. That portion shouldn't be added if you want to get the same value. So what I'll do is I'll just subtract off the amount of that integral that flowed across the boundary. I'll call that delta F in. And then there's some of the blue material that flowed out of the red region during time delta t. And I'm going to call that delta F out. So that basically is, so once I do that as addition and subtraction of the portion that flowed in and out of the control volume, that actually makes that total term F, like F material at t plus delta t, that accounts for it. So it's like what's inside the control volume minus whatever had flowed in. So that portion traces out the red region. And then I need to add back, whatever had flowed out, because that was in the blue region, but it doesn't appear inside the red region. And then at time equal t, those two integrals are exact, like the material integral and the control volume integral are exactly the same, because those control volumes are coincident at that time. From there, we can identify some derivatives that are starting to present themselves and try to do a little bit of calculus work. So let me move some of this writing to the next page over. All right, using the miracle of video editing, I have moved all of that image and the equation over to the next page. So let's try and set up some derivatives here that actually look like something we can work with. So if I highlight the two control volume terms that are sitting there, the two with the red underscore CVs, one of them is at t plus delta t and the other one is at time t, and they're all divided by a time delta t. So using calculus, we recognize that that's the derivative. So if I take the time derivative of f sub cv, what that means is the integral over the control volume of little f dv. So I have identified what that term is, and then I need to do a little bit of work to figure out what's going on with these in and out terms. So if I just look at the way that they're structured, it looks like what I'm supposed to do is subtract the rate at which the stuff flowing in across the surface is changing with time. So let's figure out what that first term is. So the term that has to do with the rate of change of things flowing in through the boundary per unit time, that really has to do with, you imagine that the value of f is fixed on the, let's say, the outer surface of the red hashed line, and what I care about is the rate at which new volume flowed into and across my control volume. Well, we've seen before that the volumetric flow rate across an interface is just v dot n dA. In this case, we need to be a little bit careful because the material and the control volume are moving. And so it's not just v dot n dA, that would be the rate at which the material moves. But since our control volume is also moving, what really matters is the relative rate between them. So the relative rate at which fluid goes across our boundary is v minus the control volume velocity dot n dA. So in this case, I'm interested in two integrals. One that has to do with how much volume flowed into and across my red dashed interface. And then the other integral represents how much flowed out, which is another surface integral of, actually it turns out the same thing, but only in the portions where things are flowing outwards. Well, it turns out that because the unit normal is always defined outward, keeping track of the plus and the minus sign associated with the inflow and the outflow is not necessary, because n dot v is a negative number when it's an inflow, and v dot n is a positive number when it's an outflow. And so the positive and negative signs associated with inflow and outflow sort of take care of themselves, and you don't really need to keep track of them. And I wrote it a little bit late on this this document, but just to be clear, v sub r is the relative speed, or the relative velocity between the fluid, so that's v underscore or v tilde, relative to the control surface. So it's v minus v sub cs. That is the definition of the relative velocity. So if I take the time to actually write all, just in summary, the rate of change of the integral, the volumetric integral over the material, which is the thing that shows up in our conservation laws, can be written as the sum of two integrals that are done over our control volume. So the first term is the rate of change of, our capital F over our control volume, which can also be written as the integral of little f over v, plus a second term which has to do with how much stuff flowed through the surface, which is the integral over our control surface of f times the relative velocity dotted with n dA. So that is our most general form of the Reynolds transport equation that we'll be working with for the rest of the semester. So we'll be applying this equation to conservation of mass, conservation of linear momentum, conservation of angular momentum, conservation of energy. I think that's the only ones. But as you'll see, that this is a very general way of relating our conservation equations, which have to do with integrals over fixed amounts of material, to integrals over control volumes and surfaces that we get to choose that are convenient for the geometry that we're working with. Now, that is our most general form of the equation. So, the rate of change of the total integral of the material is equal to the rate of change of that same integral but over our control volume, plus a convective term through the boundaries that uses the relative velocities. But most often, not always, but most often, we'll try to work with control volumes that are fixed in space when we can, so that the control volumes aren't moving. That will make things easier most of the time. In that case, since the control volume and the control surface themselves are not a function of time, the first derivative there can come inside the integral and become a partial derivative of the the quantity that's inside the integral. And for the control surface, we'll no longer need to use a relative velocity because, well, the velocity of the control surface will be 0, and so you just need the velocity of the material. So the fixed control volume form looks like the one in the box here. But let's take a look and compare that to Leibniz rule. So before I did all of this, I showed you Leibniz rule. So Leibniz rule said that the rate of change of f, where f was the integral of f dx from a to b, where a to b could move, was equal to what happened when I took the partial derivative inside the integral, fixing a and b, plus a set of terms on the boundaries where, let's see, the first term was you add a portion where f is evaluated at the boundary, and there's times dB dt, which is the velocity of, let's say, the right boundary, and then you subtract off a similar term which has to do with fixing f on the surface of the left boundary, and the velocity, times the velocity of that left boundary. You have to subtract that portion off. So you'll see that Leibniz rule is actually identical to the Reynolds transport theorem in the special case where the control volumes are fixed and you're in one dimension.